Okay, so we talked about the theory of training of a neural network, how we train a neural network. Especially, this is so important to understand overfitting, how to get rid of the overfitting problem, how to resolve the problem of overfitting, and also the connection between a neural network and logistic regression and linear regression that I just talked about. So remember that these are some important questions that you will see in many job interviews, because sometimes the interviewer wants to see if you understand the concepts and theory of neural networks, or you just know how to run some codes. That is why these are some popular questions. Okay, now I want to talk about backpropagation. Backpropagation is a systematic method to train a neural network. So, as I mentioned, I will do three different things to teach you how to train a neural network. The first one was the theory behind that we covered just now, and then backpropagation, which is a systematic way of implementing number one. I'm gonna talk about that now, and later in next videos I am gonna show you how to do that in Python libraries. Okay, so backpropagation, as I mentioned, is a systematic method to train a neural network. Suppose that I want an algorithm, a structured algorithm for training a neural network based on the theory that we just learned, and backpropagation will give it to us. Backpropagation is an iterative method. It's also called backward propagation. It's a very popular method for training artificial neural networks, and it's usually used in conjunction with minimization methods like gradient descent. It has two main steps or two main phases. In the phase one, so suppose that you have a network. Okay, you have a neural network, and the weights are completely initialized randomly. Okay, so you have a neural network, there are some weights here that are randomly initialized with some random numbers. And then we have some training data. We want to train this neural network based on this data. So we have some inputs and some outputs. So in the first phase, a training data, X, is provided to the network, and we move forward in our network using those random weights to create an output. That's it. So this is a forward propagation part. And then when you create that output based on this input data and based on those random weights, you compare this output that you just created with the actual output. Okay, the actual output, because this is training data, this is supervised learning, so I know the actual output, the desired output. You compare this created output with the desired output, and of course the error will be very high at the beginning because I used completely random weights. So at the beginning the error will be high. I measure this error, I mean the differences between these two. You can use one of those cost functions that we just defined to find this error and find the gradient of that, and then backpropagate this error gradient into the network. So it's like moving backwards in the network, and this time we backpropagate this gradient error that we had into the network, moving backward. Using the same weights, and we update the weights during this process of backward propagation. Well, the idea, intuitively, if I want to explain the idea, it is like calculating the error and backpropagate the error into the network and see what the contribution of each weight or each neuron is in creating this error. And based on that contribution, I update the weights. So look, this is the network. Okay. This is my network. I provide an input data, training data. I forward propagate the input data into the network, and I'm here now. I have some outputs based on this input data and these random weights, whatever weights are. I compare this output with the ideal, the desired output, y, measure the error, calculate the error gradient, and then backpropagate the error gradient into the network backward. Okay. To see what was the contribution. It's like backpropagating the error into the network. It looks like you want to see what was the contribution of each one of these neurons and each one of these weights in creating this error, and then update those weights based on that. So this systematic way is called backpropagation. So this was the main idea. This is the procedure. I will go over the procedure and then I will show you several examples and also numerical examples so that you completely understand the idea. So, step 1, randomly initialize the network with some random weights. So we start with random weights, that's fine. Later in deep learning, I will tell you that there are some better, more smarter ways to do it. Rather than starting with random weights, there are some smarter ways to do it. We will see it later. After this, step 2, apply one training sample as an input to the network and propagate forward until you find the output at the output layer. Okay. Step 3, calculate the error at the output. Okay. So you generated some output right now by forward propagating this input, but you also had a desired output to predict, which was actual output. We have it for our training data. I compared this to using a cost function that we just talked about and create some or measure some error and then gradient error. So for sake of simplicity, if we assume that this is our simple cost function, then this will be our gradient error. It's a derivative of that. And again, you don't need to remember these equations. I will provide to you if you need to use them. After that, you backpropagate this error gradient error backward into the network and update your weights. Okay, so this is your new weight, this is your old weight, and this is the update part. So we did this before for linear and logistic regression. This is just taking one step, right? This is the same thing that we had before, in fact. So in that one, we in gradient descent, we take one step to update your theta, you remember? And we had a factor here called learning rate that make the steps faster, your pace faster or slower. This is learning rate. So this is your old weight, this is the new weight, and this is the size of a step, one step that you take to update your weight. And this is the step size, and this is a factor that adjusts your step size. So we had this before, okay? So these are the main idea. Is the same thing, just backpropagation is a systematic way to implement those techniques. So we update the weights and backpropagate error. Look, I just moved to the previous layer. Okay, so this was layer L. This is layer L minus 1. You don't need to remember this equation because in fact this is equivalent to moving backward in the network. Whatever your network was, for example, 1 neuron here, 2 neurons here, this summation and everything is like moving the error at this level. This is level L, and at this level this is L minus 1. I move backward in the network and update the weights. Okay, and do it for one data sample and then repeat it for another data sample and another data sample. All of my training data samples, and if I go over this process, your neural network will be completely trained. This is called backpropagation. It includes two main steps. When I provide a training data to my network, I move forward to create output. I measure error, calculate gradient error, and then backpropagate the error into the network and update the weights. Okay, and then I go to the next training samples, do the same thing, create output, measure error, backpropagate error, update the weights. Okay, and next training samples. I do it for all of the training samples, and after that these random weights will be converted to the normal weights that can make the best prediction for us based on this training data. Okay, so now I want to show you one example how it works, and then I want to show you a numerical example. Okay, so suppose that this is one network. Okay, this is one. So please listen carefully. I am showing you how to do one step of backpropagation using only one training sample. So suppose that this is X is one training sample, and I'm showing you how to do one iteration of backpropagation. Okay, so X is my input data, my features. I forward propagate it in the network. Okay, so notice that just for the sake of simplicity, I ignore the bias here in this picture, but we have it anyway. We have it. Doesn't matter, just for sake of simplicity. So these are some weights, let's say random weights. I call them W11 and W12. So A11 will be this, of course, G of W11 times X1 plus W12 times X2. And then similarly, I'll calculate A2. And similarly, I'll calculate A3. So of course, A3 again will be like W31 X1 plus W32 X2, and then G of that. Okay, there we go. So now I have I have A1, A2, A3. I continue to the next layer. So the outputs of the first layer will be the input of the second layer. So A12 will be G of this guy times this, plus this one times this, plus this one times this. Here you go. And similarly A22. And after calculating A1 and A2, I continue to the next layer. Again, the output of the second hidden layer will be the input of the next layer. So A13, which is also our output, right? This is our output, is equal to G of this guy times this plus this one times this. Okay, so this is called forward propagation. So I had the input data X, I forward propagated that data into the network and created an output O. Okay, step 2, I find the gradient error. So this is your output, this is your desired output. This is what you just created, this is what I want to create, this is my prediction. So I find the gradient error using this formula, which is in fact the derivative of cost function. And so this is this guy, gradient error at this level. Okay, I just calculate that using this formula. And now look at this, I just backpropagate this backward into the network using the same weights that I had from before. So this was delta 1 3, so this guy will be delta 1 2, which is this one, backpropagate into the network. And again, this one backpropagate into the network will be this one. I have this term because this is the a derivative of sigmoid function. So assuming that my g function is sigmoid, I will have this part from the chain rule of derivatives. I will create this part as the derivative of the sigmoid function. But this is the main idea. I have error at this level, and now I backpropagate error into the network. And when I backpropagate the net error, I update my weights. So this was the old weight, this is the new weight. This was the old weight, this was the new weight of the network. So now I have new weights and continue backpropagation. Now I have error in this level, gradient error in this level. Again, I backpropagate that, the error backward, find the error at this level, and then update this weight and this weight. So I started with completely random weights, and then I backpropagate the error and update these weights again. Next layer, I update these weights. So again, the idea intuitively, it totally makes sense, and it is simple. I provide the network with the data sample, I move forward, I create an output. So I desired an output. Why? I wanted this, but I created this. Of course, error is high here because I use some random weights at the beginning. As I trained the network more and more and more, the error will be smaller, of course. But at the very first step, the error is high, and I want to see what was the contribution of each one of these neurons in creating this error. So I backpropagate the error, and based on the amount of gradient error, I update these weights. Okay. And then next x, I provide next x to the network, do the same thing, and as we repeat that, and as we provide more training data and more training data to the network, these random weights will be more accurate, and my output prediction will be more accurate, and hopefully by the end of the training step, your output will be almost equal to your desired output. So this is the idea of backpropagation. This is not something new, okay? This is just a systematic, algorithmic implementation of a minimization that we learned just now to make and to train a neural network. Now, I want to tell you a fact which is very important. Here's a question. Backpropagation makes sense intuitively, but remember we wanted to minimize J function, and we had a JW cost function that we wanted to find the minimum of that. This was the theory, what we wanted to do. How come this backpropagation is same thing as this? This is the question. The answer is simple. Backpropagation is actually the implementation of this. Why do we do that? What does that mean to return the gradient error backward into the network? It is in fact the implementation of this. It's in fact the implementation of chain rule when we take derivative for this minimization. That's it. In fact, backpropagation is the implementation of chain rule. So look, when you have a neural network, okay, so each neural network layer is like a function. So I have an input layer, and then I have a first hidden layer, I call it H, and then I have another, so each one of them has some neurons, right? Some neurons here. And then I have another hidden layer called G, and then I have another hidden layer called F, and then your output. And then this is your input, okay? So in here, your output, this is your output. Your output will be, in fact, so this is X, this is H of X here. This is G of H of X here. And your output will be F of G of H of X. One more. Correct? So this is your output. So what is derivative of that? What is derivative of this output? Okay, when you want to take the derivative of F of G of H, here you go. It will be derivative of H, derivative of G of H, derivative of F of G of H. So this is chain rule of derivatives, right? This is what actually I'm doing in backpropagation, moving backward. What does that mean? Look, I go backward. It means that I move backward into calculating this guy and this guy. So by moving back the derivative, okay, in fact, I'm trying to take derivative of the whole thing. I'm taking derivative of this function, which is F of G of H. To do that, I have to first calculate the derivative of F and then go one level backward to calculate derivative of G, and another level backward to calculate derivative of H. Here you go. Derivative of F, one level backward to calculate derivative of G, and one level backward to calculate derivative of H. That is why I move backward in the network. In fact, all of these things that we learned so far, the backpropagation, is just taking derivative of your output to find the minimum of J function, which was your cost. To do that, I need to take derivative, and backpropagation is the systematic, algorithmic, very smart way of implementing this chain rule of derivative. Okay, so this is the idea. Okay, so I have one numerical example here that I want to show you. And using this numerical example, it will help you to completely understand how a network and backpropagation works. This page is very helpful. So I created this page. I call it summary backpropagation in one slide. Okay, that gives you the very quick brief instruction how to implement the backpropagation simply in just one slide. So randomly initialize the network, apply one training sample as an input, propagate forward, calculate the error at the output, okay, backpropagate the error into network, update the weights, okay. So this is one slide, explain everything. But again, you don't need to remember or memorize these equations. You will be provided with these anytime you need to use it. This is our numerical example. Suppose that we have this network. This is one training sample. Okay, this is one training sample, X and Y. So Y 0.5 is the output, the desired output, and X is the input. It has two features. This is X1 and this is X2 and this is Y. Learning rate is 1. I randomly initialize the network with these random numbers and I want to train it using one single sample. So this is, look at this, X1 0.35, X2 is 0.9 and output is 0.5. I provide these two samples to the network. So this is X1 and X2, my training data. This is my training data. I want to train the network using this training data. I provide this sample to the network and move forward. So this is G function, sigmoid function that you use. I find A1 and A2. So as you see, A1 is G of this. I just put the numbers here. So for example, W11 is 0.1, W12 is 0.4, X1 is 0.35, and X2 is 0.9, and so on. So I just put the numbers and calculate G. So this is what I have. Output of A1 and output of A2. Now these two will be the input of the next layer. So I provide these two to the network and output will be 0.69 at this level. This is the output that I created using these two inputs and using these random weights. But this is what I want. This is the desired output. So I have error here. I use this equation to calculate error gradient. So this is the error that I have at this level. Okay? This is error. Now it is time to backpropagate this error into the network. So moving backward. I move the delta backward to the network. Here you go. So if you move the delta backward into the network, I change the direction of these arrows and change the color too. So it was forward, now it's backward, and here you go. So these are the values. I've just put it there. So these are gradient errors in the previous layer. And now I update my weights. I have to update this weight and this weight using this formula. Here you go, here you go. I updated them. So it was 0.3. Now I change it to 0.27. It was 0.9. Now I updated that to 0.87. So as you see, I made a small change in each one of them using only my first training data. So I had one training data provided to the network, and based on one training data, I updated the weights a little bit. And now I continue, I backpropagate this error into the network and update the weights in previous layer. I mean these 4 weights. Here you go. So these were my old weights. This is a new weights. So this is the update that happened only using one training data sample. So I provided x1, maybe my first training data sample. This is my desired output, and based on this I updated my weights. It is like providing the image of one dog to a kid's brain, and by using one sample, looking at one data sample, he updates the brain. He updates the wiring of the brain a little bit. Now you can provide another picture of the dog, another picture of the dog, another picture of the dog. And by providing each picture, you update these wirings and learn. Okay, so right now that I'm talking to you and you're listening to me, you are changing these weights of those connections in your brain, and you're learning something. Okay, so every word that you hear, every picture that you see, in fact, make these changes in your brain. It changes the weights of those connections in your brain. And here we have only 6 of them. In your brain you will have billions of them. But the same thing, the same idea. Each time you provide one data sample to your network using this propagation technique, you just update the weights a little bit. And this updating these weights and changing these weights is learning. This is how our brain learns. This is how a neural network learns. Now, next sample, next picture of the dog, next data samples in your training sample, whatever the data is, doesn't matter. You provide x2, again, update this guy. And this one, maybe after that, it will be like 26, or this one will be like 85, and so on. And then next sample, x3, again this one will change. Okay, and then after providing thousands of samples or tens of pictures of dogs, then your brain learn what does it look like. This is the idea of learning, how our brain learns and how you train your neural network. So this is all for today. Today we talked about training. We learned almost a lot of things about how to train a neural network. We talked about the theory of minimization, how to minimize the cost to train, and then we talked about backpropagation, which is a very efficient, practical, and systematic way to implement those minimization. And I told you how backpropagation makes sense intuitively and why it is an implementation of that minimization by implementing the chain rule of derivative.